Hello everyone, thank you for joining me today as we discuss sums, area, and the definite integral. We have two objectives today: to connect summation notation with a definite integral, and to use properties of integrals and area formulas to evaluate definite integrals. But to build up to that idea of a definite integral, we've got to connect to the past. So previously, we estimated the area under curves using rectangles. In the image shown below, we have an example of a right endpoint approximation with 4 rectangles, and clearly that's going to underestimate the true area under that curve. The thought is then, how could we improve that estimate? And the answer to that thought is to use more and more rectangles. So here's a demonstration. Here we're finding the area under this curve from -1 to +1. In red there it says that the exact value of that area is 3.333. Right now I'm using a Riemann sum with one big rectangle and I'm getting an answer of 2. Clearly that's not a very good estimate. If I use a few more rectangles, 11 rectangles now, we get an estimate that's better, 3.322, but the true area is 3.333. Well, if I continue to use more and more rectangles, you can see on the image here that because we're using more smaller width rectangles, we're able to fill in that area a little bit better, a little bit more precise. And as I increase the number of rectangles, you can see here, we've already hit that true value, or it's so close that this calculator can't determine the difference between the two. So this was supposed to show you that if we increase the number of rectangles we use in our approximation, we're going to get a better estimate of the true area under that curve. So how does that lead to this idea of a definite integral? Well, here's how. Let's suppose we do a Riemann sum approximation and we use n rectangles. The thought is we're adding up the areas of all those rectangles, right? Well, the area of those rectangles will be the base times the height of that rectangle. Now, the heights will be different, and so I'm going to use a subscript there to indicate the different heights, the height of the first rectangle, the second rectangle, the third rectangle, all the way to the nth rectangle. And remember, we're adding all of these area calculations together, and in mathematics, we have a system for that. A construct for that, and that is this summation notation. We are adding up a sequence of terms, we're adding up a series here of area calculations. Now here, we're starting with the first rectangle going all the way up to the nth rectangle. Okay, I is starting at 1, so the first rectangle, then 2, the second rectangle, all the way up to n. Maybe n is 10 rectangles, 100 rectangles, whatever it may be. Well, if using more and more rectangles is going to give us a better and better estimate, let's not stop here and just use n rectangles. Rather, let's use a calculus construct to get an even better estimate. If using more and more rectangles will give us a better estimate, let's let the number of rectangles approach infinity. Let's use a limit here. And this starts to head towards the definition of a definite integral. This is the idea behind finding the true area under a curve, using this limit of a sum. Now this notation, while it's good mathematical notation, it is perhaps not as streamlined as it could be, maybe not as user-friendly as it could be. So thankfully, we have some notation that is a little bit more streamlined, and that is this definite integral notation. So here we have reached this idea of a definite integral. The definite integral of f of x from a to b is describing the area under that curve f of x, bounded by the x-axis and the vertical lines x equals a and x equals b. The image below there shows that area under the curve. The notation that we use for a definite integral is shown in the red box below. On the right-hand side there, you can see a version of the summation notation that we had written. On the left-hand side, you can see that new notation for us, that definite integral notation. I want to talk quickly about the connection between these two just a little bit. You can see this dx is acting a little bit like the delta x here. F of x is acting like the f of x subscript I. Remember, these are the heights of the rectangles. This is that base that is the same, okay? A little bit more about this delta x here. That delta x is the width of the rectangles. And remember, we can calculate that if we take the length of our interval and divide by the number of rectangles. So that just shows the connection between a, b, and that delta x over here. So we have our definite integral notation. This symbol for an integral is this elongated looking S-type shape. think S for sum. We are summing up the areas of a bunch of rectangles. So think of that symbol that way. A and B are the lower and upper limits of integration. Basically, where are we starting to accumulate area and where are we ending that accumulation? F of x is called the integrand. That's the curve whose area we are finding. Dx is the variable of integration. And when we find the value of that integral, when we find that area, we have then evaluated that definite integral. So this is not a main idea per se, but I think it could be helpful to at least try a few examples where we take a Riemann sum using that summation notation and rewrite it as a definite integral. So let's start here with this example. This looks maybe a little bit complicated, but let's get our integral symbol down first. Here are the lower and upper limits of integration, starting at -2 and going to 6, right? In terms of our integrand, it looks like the heights of our rectangles are given here, where c subscript k is being cubed. Well, if it's being cubed, then our function here, our integrand, must be x cubed, and that delta x, the width of our rectangles, coincides with our dx. So there it is, written as a definite integral. Let's try this one. Let's get our symbol down first. Our limits of integration are 0 and 3. Our integrand here looks like 2x squared minus 5x, and our delta x there is our dx. One more with you here. Our limits of integration are pi and pi over 2. Notice the upper limit is technically less than the lower limit here, which is kind of strange, but we'll talk about a property for that in a moment. In terms of our integrand, 4x minus sine squared x is what I see here, and our delta x there gets filled in with our dx. Not the biggest idea, but still important for us to be able to connect the summation notation to the definite integral notation, at least a little bit. Couple thoughts here about those definite integrals before we start evaluating some using some properties and some geometry formulas. Let's talk about how continuity connects with the existence of a definite integral. And theorem 4.4 on the slide here shows that if a function f is continuous on the closed interval a to b, then f is integrable on a to b. That is to say that the definite integral from a to b of f of x dx exists. So here is an existence theorem telling us about how continuity connects with the existence of a definite integral. So, how are we going to go about evaluating these definite integrals? Well, later in chapter 6, we'll learn how to do this using a technique of antiderivatives. But for us right now, we need to start just by making that connection with area using area formulas from geometry and then also some properties of definite integrals. So take this function f of x, looks like some sort of piecewise function made up of a few triangular shaped regions and then what appears to be a semicircle there. We're going to evaluate all three of these definite integrals. But before we do, a quick note about the image in the top right. When we evaluate definite integrals, when we find area under the curve, if that area exists above the x-axis, we consider that to be a positive value. If that area exists below the x-axis, we consider that to be a negative value. Think about a velocity curve when it goes below the x-axis. When velocity is negative, okay, then the object is moving backward. Well, then in terms of position, that's a negative accumulation happening there. So that area is considered negative. Okay, take that for what it's worth at the moment. But let's take a look at this definite integral from 0 to 2 of f of x dx. Well, from 0 to 2, that's this area that I just shaded in, and it is below the x-axis, so we'll treat that as a negative area. And that's a triangle with a base of 2 and a height of 4. So here we go. It's negative because it's below the x-axis. 1/2 base times height, 1/2, 2 times 4. Again, treat it as negative because it's below the x-axis. How about the definite integral from 4 to 6? That's this area here. Looks like a quarter of this circle. Well, if it's a quarter of that circle, let's use the circle formula and multiply it by a quarter. The radius of this circle appears to be 2. So 1/4 pi times 2 squared. That will result in exactly pi. Now the last definite integral spans all the way from 0 to 9. Well, Let's use what we've already found. We already found this to be -4. We found this to be pi, right? Based on the symmetry of this semicircle, this area should also be pi. So without doing hardly any work at all, I've already found the area under the curve from 0 to 6. So now to go from 0 to 9, we just have to add this last triangular region here. So let me write this down now. We have the -4 from that first chunk. Then we have a couple of pi's. Now we need that triangular region with a base of 3 and a height of 1. Now I just add all of these together. I could give it specifically as a decimal, but I'll keep it in terms of pi. And when I combine -4 with that last triangle, we'll get -2.5. So here we have evaluated all three of these definite integrals just using commonly known geometry formulas. Fairly convenient that this function was made up of a bunch of such shapes, and it will be for the time being until we learn about that technique that involves antiderivatives. Another technique that we can use to evaluate definite integrals, though, are using some properties of definite integrals. I'm going to go through a couple here, and they all have names. Whether you remember those names or not is not incredibly important, but we will use these to help us actually evaluate some integrals here in a moment. Starting with the zero property for definite integrals, if we integrate from a to a, then we have not accumulated anything, and so the value of such a definite integral would be 0. There's a constant multiple rule for definite integrals, just like there was a constant multiple rule for derivatives. Bring that constant out in front. If you have the definite integral of a sum or difference of functions, you can split that into the sum of the definite integrals or the difference of the individual definite integrals. Finally, the order of integration on this slide, if we switch the lower limit and upper limit of integration, then the result we get is the opposite of the original answer. It's kind of like we're integrating or finding area accumulation backwards, and so we get the opposite answer for that. Just a few more here. We used this additivity property on that last geometry example we did, where we split that into a bunch of chunks and then added those chunks together. That's what this shows, and I think the image describes it fairly well. Finally, the domination property here, if f of x is greater than or equal to g of x for all x, in other words, f of x is taller than g of x, well, then the area under f of x is going to be greater than the area under g of x, because f of x is taller. It's got more area under it. That's the domination property for you. We're going to use these properties to evaluate some definite integrals. So here goes. Given the information above, we've been asked to evaluate 4 definite integrals here. We don't have the graph of f, so we can't use geometry formulas. We're going to have to use our properties. So here goes, letter A, the definite integral from 0 to 7 of f of x dx. Well, we are not given that specifically up above, but we are told that from 0 to 5, the area under f is 10, and from 5 to 7, the area under f is 3. So if we just add those two together, 0 to 5, 5 to 7, that will give us the area from 0 to 7, 10 plus 3 being 13 here. There's that additivity property. Letter B, the integral from 5 to 0 of f of x dx. Well, we know what the integral from 0 to 5 is. That's 10. So using our order of integration property, then this would be the opposite of that, negative 10. Letter C, the integral from 5 to 5 of f of x dx. Well, the lower limit and upper limit are the same, and so we are not accumulating anything there. Finally, letter D, the integral from 0 to 5 of 3 f of x dx. That's a constant multiple that we can bring out in front here. So just take 3 times the definite integral from 0 to 5 of f of x dx, which was 10, giving us a final answer of 30. There's a few properties we haven't used yet, though, so let's do one more example here. New information given to us there. Letter A, the integral from 2 to 6 of f of x plus g of x dx, right? Okay, here's our sum rule. We have the definite integral of a sum of functions. We can split that into the sum of the individual integrals. From 2 to 6, the area under f is given to us as 10. From 2 to 6, the area under g is given to us as negative 2. So collectively then, we have 8 for that value. Letter B now, same kind of idea, but this time a difference. The area under g of x from 2 to 6 is negative 2. We are subtracting the area under f of x from 2 to 6, which was 10. giving us a result of negative 12. A couple more. This is that constant multiple rule again. Bring the 2 out in front. This will be 2 times the definite integral from 2 to 6 of g of x. That's 2 times negative 2 here, which is 4. This last example, letter D, is a combination of some of these properties. We can take 2 times the area under f of x from 2 to 6, subtract 3 times the area under g of x from 2 to 6. I'm being a little bit loose with how I write this here, and combine all of this to get an answer of 26. So there we have used most of the properties listed in order to help us evaluate definite integrals. There was a lot of information provided here today. Tried to skim over it as best I could while still keeping a good pace. That's enough today about sums, area, and the definite integral. Thank you for watching.